In this video, we will look at the reactions of alkenes. So alkenes undergo an electrophilic addition mechanism. So in order to understand this mechanism, you need to know the differences between a nucleophile and an electrophile. So we'll briefly go over the differences here at the beginning. So we'll start with a nucleophile. Nucleophile is nucleus loving, which usually means that they're going to be negatively charged, and they're always going to be a Lewis base. So you're looking for a lone pair or some other electron-rich part of a molecule, so maybe a pi bond or a lone pair or a negative charge, that part of the molecule will function as a Lewis base and nucleophile, depending on the situation. And the reason we say they're nucleus loving is because this lone pair or pi bond or whatever our electron-rich region of the molecule is, it has a lot of negative charge, it has a lot of electrons, so it's going to be attracted to positively charged things like a nucleus. So that's why we say nucleophile is nucleus loving. All right, so then the electrophile is next. Electrophiles are electron loving. They're usually positively charged, and they're always a Lewis acid. So similar to our explanation of the nucleophile, if we were going to have a Lewis acid, that is likely to interact with the electron density of the Lewis base, the large amount of negative charge. So that means that the electrophile is going to then be positively charged most of the time. It's always going to be a Lewis acid, and by definition, it just has to have the ability to take another bond from the nucleophile. The nucleophile and the electrophile will form a new bond between the Lewis base and the Lewis acid. So this is the first part of understanding these types of reactions, is you have to quickly look at the species that you have and identify what is your Lewis base, which is your nucleophile, and what is your Lewis acid, which is your electrophile. So let's take a look at the electrophilic addition mechanism. So we have this generic reaction where we have this alkene reacting with some molecule AB that makes the alkane that is now disubstituted with A and B on what were the alkene carbons in our starting material. So one thing I want to point out, this alkene happens to be tetrasubstituted with these 4 R groups, but these are just generic placeholders that I'm putting there. They could be a hydrogen. It's not necessary. The only key part that is necessary for these types of reactions is that you have a carbon-carbon double bond, which is the alkene functional group. If you have that, then you can undergo this type of reaction. So the first part to begin this mechanism is to identify what is our nucleophile and what is the electrophile. So we have this pi bond, this carbon-carbon double bond in the alkene that is electron rich. So this is likely going to function as our nucleophile. And then we have some molecule AB, where A is different than B. This could be like hydrochloric acid, HCl, or HBr, something like that, there's a difference in electronegativity. So B is more polar or more electronegative than A, so that causes this dipole away from A and towards B, which causes this permanent dipole of the distribution of charges. So A is going to have a partial positive charge, and B will have a partial negative charge, meaning that A, with its partial positive, can function as an electrophile towards our alkene nucleophile, which is the exact first step of the mechanism that we'll see here. So we have our carbon-carbon double bond. That is going to function as our nucleophile. So in blue, what's shown is we're creating a bond between one of these carbons using the pi bonds to atom A. And then at the same time, the AB bond is breaking onto B. The reason that this part is necessary is, let's consider that A is a hydrogen, like I mentioned here. If this is HCl, well, A hydrogen couldn't take a second bond. It would be violating its maximum number of bonds that it can have. Hydrogen can only have one because it only has access to the first energy level, so the s orbitals. So because of that, you need to break this bond at the same time that you're forming the bond to A, to the hydrogen atom, for example. So at the same time, which carbon is A binding to? And the way that this is drawn, it could be bound at either one. And that is key for predicting the types of products that these undergo, because there may be a difference in stability of the product that's made if the A atom were to bind at this carbon versus this carbon, and we'll investigate that. But as a generic example, I'm just going to say that you're creating this bond between this carbon and this A atom while breaking the AB bond at the same time. So what happens in that case is we create this, what I've marked as this blue bond, where we create a bond between this carbon and A. And at the same time, we now have one less bond to the carbon on the right here, which then requires that it becomes a carbocation, which is a positively charged species where the positive charge is on the carbon, hence carbocation. So carbocations are planar. So what that suggests is that a new nucleophile could attack it from above or below the plane, creating different stereoisomers, and we'll investigate that here in a second. But after we create this bond, we're also breaking off this bond of the AB bond to form B minus, which is this molecule here. So now in the second part of the mechanism, we now have an electrophile, which is this guy with a positive charge on the carbon, and a new nucleophile, which is B minus. It could be like a halogen, for example, or a water molecule or something like that, that can attack and create a new bond between the Lewis acid and the Lewis base here, which creates the final product of carbon, this alkane with A and B bound at both of the alkene carbons. So what I mentioned here is that this is planar, so the B can come from below the plane or above the plane, meaning that you would make the enantiomeric mixture of this final product. There would be no stereoselectivity in the final answer. It would just be a racemic mixture of multiple products. So the other thing to mention is this seems to suggest that there may be a preference at which carbon the A atom should bind to, and that is the next thing we'll investigate. In this general example, there's no difference, but there, in specific cases, there are explanations for why a particular product would form over another. Here is the complete list of carbocation stability. So one thing I want to point out, I'm not going to explain why this is the ranking in this video. I'll save that for another video, but we're simply going to use the ranking to predict our products for these types of reactions. So the general rule is the more substituted a carbocation, the more stable it is. So what I mean by that, by more substituted, is the more carbons that are bound to the carbocation center, so the one that has the positive charge, the more stable that is. So if we look at our primary carbon, this is a carbon bound to just one other carbon. That was why we consider this primary, so that is not very substituted. Secondary is substituted once more than the primary, so this is more stable, and our tertiary is substituted an additional time over the second, and that is the most stable of all of these. The other ones that we have here, like benzylic, allylic, vinylic, and methyl, have other reasons governing their relative stability that I'll touch on here briefly. So our methyl is the least substituted possible. This would just be simply methane with the loss of a hydrogen to form the carbocation. This is not substituted at all, so this is why this is the least stable among our primary, secondary, and tertiary list. And then vinyl. Vinyl has the carbocation on the alkene, which is particularly unstable, and I'll get into that more in a different video, but just know that this is the least stable of the options. Allylic and benzylic both have resonance structures that can form that stabilize the positive charge, so that explains their relative stability. For the remainder of the video, I will work through a few specific examples explaining the approach and thought process behind solving them. So in this case, our question is predict the product and explain its formation. So in organic chemistry, whenever you see explain its formation, we simply mean to show a mechanism that explains the major product's formation, or the product that you're predicting will form, show the mechanism that explains why that forms, and potentially give a short reason for why you're predicting that formation over some other alternative. So if we look at this, in any question like this where you have to identify the mechanism, you should look and see if you have a Lewis acid and Lewis base that may function as an electrophile or a nucleophile. So here we have an alkene that is definitely going to function as a nucleophile because it has this electron-rich region where the pi bond is, the carbon-carbon double bond, that can create a new bond to a new molecule to an electrophile through an electrophilic addition type mechanism. So if we look at HCl, HCl is polar. It has a dipole moment towards chlorine because chlorine is more electronegative than hydrogen. So the chlorine has a partial positive and the chlorine has a partial negative, excuse me, and the hydrogen has a partial positive because the dipole is moving from hydrogen and towards chlorine. So what this means is our hydrogen can function as an electrophile because it has this partial positive charge. So with that then, we can show our first step is the formation of this new bond between the nucleophile and the electrophile. So I'll redraw this just to be deliberate with the bond forming and cleaving. So here now our carbon-carbon double bond will function as our nucleophile, and that will form a new bond to the hydrogen and at the same time cleave this hydrogen-chlorine bond onto the chlorine. So what that will do is create a carbocation and Cl-. So we have to determine which carbocation, if either, is more stable. So the hydrogen can add either at carbon 1 or carbon 2. So let's say that it adds at carbon 2 first, just as an explanation. So here is carbon 2. Here's our new bond that was formed between carbon 2 and a hydrogen. So that leaves a positive charge on carbon number 1. And at the same time, we form, we now have to consider the other possible intermediate where the hydrogen binds at carbon 1, forming a carbocation at carbon number 2. So again, here's carbon 1, 2, and the new bond that was formed is between this hydrogen and carbon number 1. And we also form Cl-, which has a negative charge now because of the additional electrons that were dumped onto the chlorine when this hydrogen-chlorine bond was broken. So keep in mind there are 8 total electrons around this chlorine. I'm only showing the 2 that were involved in the mechanism. So now at this point we need to evaluate our carbocations. We have a primary carbocation and a secondary carbocation. So the secondary carbocation is more stable, it's more substituted, it will be the predominant intermediate. So this will not form, just put an X there, and this will form in much greater quantities. So now we have to finish this mechanism, and we have a new electrophile, which is our carbocation, and a new nucleophile, which is the halogen minus, the Cl minus in this case. And that will form a new bond between the carbon here, carbon number 2, and the chlorine. So, like I've shown there, this lone pair is used to create the new bond. This one here. That is the new bond between the chlorine and carbon number 2. And that will be the primary product. This is, in fact, you'll see more than 99% of the product in this case will be this particular major products because this is so much more unstable. The primary is so much more unstable than the secondary. So the only correct answer to our question above, which was predict the product, is this one. And now, for a second, let's think about the chirality or stereochemistry here. I've mentioned in this video that the carbocations are trigonal planar, which means that the new nucleophile, the halogen in this case, can attack from above or below, meaning that the chlorine will be a dash or a wedge in this position. But this molecule is achiral, right? Because there's 2 methyl groups to that carbon, making that achiral. So you don't have to specify that this is a racemic mixture or anything like that in this case, because it's not. You're only making an achiral molecule, which is this 2-chloropropane that is it doesn't matter if this is a dash or a wedge because all the bonds can freely rotate and there's no difference in three-dimensionality. So this is achiral, so this is simply the answer, and this is the mechanism that explains the formation for this product. If you wonder why there's no hydrogen shown here at carbon 1, it's still there. I'm only showing it in this representation to explain that that hydrogen came from the HCl in this first addition step. Here we have another question in which we're looking at a cyclic alkene instead of a non-cyclic alkene, but the chemistry is very similar and we'll walk through it. So again, the question is the same: predict the product and explain its formation. So show the mechanism. So we have our carbon-carbon double bond. This is going to function as our nucleophile, just like it did in the previous question. And we have HBr, which is another polar molecule. The dipole moment is towards the bromine, away from the hydrogen, making the hydrogen partial positive and the bromine partial negative, meaning that the hydrogen can function as the electrophile. Very similar to the question we just looked at. So now I'll redraw this after we identified everything and go through the first step. Okay, so here we have our electrophile, which is the halogen, is the hydrogen, and the nucleophile is our alkene. So we have a bond forming between our nucleophile and our hydrogen. And again, this will be determined by the stability of the carbocation. So it's whether the carbocation at which one of these centers is going to be the most stable that will drive the formation of the product. So at the same time, we cleave the bromine, the hydrogen bromine bond onto the bromine, and then we get our two carbocation species. So let's say that the hydrogen adds at carbon number 1 first, which I will call this 1 and this 2. So then our carbocation is at carbon number 2, and then it can bind at carbon number 2, the hydrogen can. So again, here's carbon 1, carbon 2. So, and at the same time, we are forming Br minus, which has the additional lone pair from the cleavage of the hydrogen-bromine bond. That's shown by this arrow. So, now, which one of these are more stable? Well, hopefully it's clear at this point. It's all about the substitution. So this one is bound to 2 R groups. This is bound to 1, 2, 3 R groups. So this is tertiary, which is more stable than secondary. So this carbocation does not form nearly as much as this one because this is far more stable. So now you have a bond formed between our new nucleophile, which is the Br minus, and our new electrophile, which is the carbocation. So this adds at the carbon number 1, forming now the product. And the product has that bromine binding at carbon number 1. Now, again, the carbocation is planar, so the bromine can bind from the top or the bottom, either making it a dash or a wedge. However, this molecule is achiral as well, but it may be a little bit more tricky to see, but it has this internal plane of symmetry here, making these two groups the same as a part of the cyclic structure. The two cyclic substituents are identical, making this achiral. So you don't have to look or consider the stereochemistry again in this case because it is just an achiral molecule. There would be no difference in the three-dimensionality of the potential products. So because of that, then the answer to this question is just adding the bromine at the most substituted carbon. And again, we have the hydrogen adding at this spot that you don't have to show, but you can, especially if you're showing the mechanism, it's good to show because you know where the bonds are being formed and broken, but you don't have to show it if it's just to predict the product. But again, this is achiral, so you don't have to worry about the dash or wedge. But if it were to be chiral, you would just have a racemic mixture where you have an equal 50-50 mixture of the two enantiomers. So that is all I have for this video. Hopefully you found it useful. If you did, please leave a like and subscribe to the channel for more content like this. If you have any questions, please leave them down in the comment section below, and I'll answer them as quickly as I can. But with that, I hope you have a good day, and I'll see you all in the next video.